Earthquakes cause buildings to shake, at bilang engineer, kailangan nilang malaman kung paano magre-respond ng isang structure to the shaking in order to design safe buildings. To do that, engineers need to understand how the ground moves during an earthquake. Umpisa natin mas maintindihan ito sa pag-unawa ng basics of earthquake ground motion. Diba, during an earthquake, the ground moves in all direction, up and down or sway from side to side. At ang intensity ng paggalaw na ito ay nagdedepende sa kung gaano ba kalayo yung site sa earthquake's epicenter. And usually, yung ground motion ay minimeasure in terms of acceleration, velocity, and displacement. Ang dalawa na nga sa measurements na mahalagang makuha upang magkaroon tayo ng idea kung gaano kalakas ang force na ma-experience during the event ay ang maximum acceleration experience at the site during the earthquake o yung tinatawag na peak ground acceleration at ang maximum speed at which the ground moves or yung peak ground velocity. Pero di pa rin pala ito sapat. So, simply knowing daw the peak acceleration or velocity, hindi daw yun sapat to fully predict how a building will behave. Di lang pala peak values yung kailangan natin. Importante sila pero they don't tell the whole story. Nagbavari kasi yung ground shaking over time. And at the same time, hindi naman sa isang peak lang magre-respond ang mga buildings. They respond to the entire shaking history. So to design buildings that can survive earthquakes, kailangan maintindihan ng mga engineer kung paano magbabehave ang structure throughout the shaking, not just at its peak. So what do engineers use instead? So gumagamit sila ng tinatawag na response spectrum to capture the building's reaction to ground motion over time. Response spectrum is a tool that shows how a structure will respond to different frequencies of ground shaking. So kinakapture nito kung gaano ma-vibrate yung isang building at under various shaking intensities or frequencies. So, imagine mo yung swing sa isang playground. If you push it gently, syempre, it will move back and forth slowly lang din. Kapag naman mas napalakas or mas napabilis, syempre, gagalaw yung swing ng mas mabilis and with more force. So, imagine mo yung swing as a building during an earthquake. Yung different push ng earthquake sa ground or sa building, magkakaiba yun. Magkakaiba rin yun. Yung iba, gently lang din, pwede rin na super violent. So, different responses yung binibigay. So, pinapakita ng response spectrum sa mga engineer kung gaano gagalaw yung building under different speeds or frequencies of shaking. Kaya lang, medyo may issue. Kasi after average out yung data from multiple earthquake records to get a reliable prediction kung paano mag-behave yung building, kailangan pa rin i-smooth out kasi ang ipapakita lang ng data sa iyo is maraming sharp peaks or high points and low points. Ang mga points na ito ay magre-represent ng specific moments kung saan mas nag-shake yung building or kung kailan man di gaano. Hindi kasi nakakatulong yung sudden changes na ito in designing the building. So after ma-smooth out ang response spectrum, ang smoothed curve na ito, yun na yung tinatawag natin na design response spectrum. So, yung design response spectrum, siya na yung smoothed and simplified curve na ginagamit ng mga engineers for designing earthquake-resistant buildings. Ini-ensure ng design spectrum na masasurvive ng building ang various types of shaking, from slow vibrations to fast violent movements. So, ngayon alam na natin ang importance ng design spectrum. Dumako naman tayo kung paano develop ang unang design spectrum. So, noong 1959, George W. Hausner created the first design response spectrum. Ginawa niya ito by averaging the response spectra from 8 different earthquakes, including the major ones in California and Washington. Dahil sa ginawa niya nakapagpasimplify sa complex data na nakakatulong naman ngayon sa mga engineers, naging groundbreaking ito. Over the years, marami pang methods ang na-develop to create design spectrum. Ilan lamang ang mga sumusunod sa mga main methods na ginagamit ng mga engineer ngayon. Method 1 is using a specified peak ground acceleration in a typical response spectrum shape. Method 2 is the new Mark and Hall method, which became a widely accepted approach. Method 3 is using statistical correlations to directly calculate average response spectrum from multiple earthquake records. So, in creating response spectrum for earthquake-resistant design, ang tatlong method na ito ang nagpo-provide ng needed data. At mas i-explore pa natin ito in more detail throughout the discussion, so you can see how they help in designing safer buildings.
The elastic response spectrum is a graph that illustrates the peak response or acceleration, velocity, or displacement of a single degree of freedom or yung tinatawag natin SDOF system, subjected to seismic ground motion. It represents how the structure of varying natural periods respond to earthquakes under elastic conditions, assuming they do not undergo permanent deformation. So in figure 5.1, response of building frame to seismic ground citation involves some aspects. First aspect is dynamic characteristic. So ang dynamic characteristics is building frame has unique dynamic properties include its natural frequency, damping ratio, and mode shapes. Next aspect is ground motion. Ground motion is an earthquake occurs, ground shaking induces forces in the structures. Third aspect is inertia forces. The ground shakes, the building experiences inertia forces due to its mass. Next is structural behavior. The response can be elastic, where the structure returns to its original position after shaking, or inelastic. Next is damping. Damping mechanism such as materials and design features help dissipate energy during seismic events. Next is resonance. If the frequency of the seismic wave matches the building, natural frequency resonance can occur. And the last is design consideration. Engineers use response spectrum analysis and time history analysis to predict how a building will respond to seismic excitation. Next is figure 5.2 and figure 5.3. Displacement response to seismic ground excitation refers to the movement of a structure as it reacts to the forces generated by earthquake. So dynamic response, when ground shaking occurs, the structure's mass experiences inertia resulting in lateral displacement that can vary with the height. Natural frequency, the structure natural frequency plays a significant role in how it responds. Displacement response is a crucial of designing safe buildings that can effectively withstand earthquake forces. Equivalent static forces. This is a simplified method used in seismic design to estimate the seismic forces acting on a structure. It represents the total lateral forces that would produce a similar response to that dynamic analysis. Next is base shear. Base shear refers to total horizontal force that a building must resist at its base during an earthquake. And last is over moment. The overturning moment in the moment that tends to rotate a structure around its base due to lateral forces such as those generated during an earthquake. It calculated as the product of base shear and the weight of which the forces act.
Everyone, ngayon naman i-discuss ko yung Elastic Design Response Spectrum. So this tool plays a vital role in how we design buildings and other structures to withstand earthquakes, ensuring they remain safe and resilient during seismic events. In this presentation, I'll explain what the Elastic Design Response Spectrum is and how it works and how engineers use it. Ano ba yung Elastic Design Response Spectrum? Elastic Design Response Spectrum is a graphical representation that shows the maximum response of a single degree of freedom system to a particular ground motion. Kapag sinabi nating single degree of freedom system, it is a way of modeling how something moves. So imagine nyo may isang bagay o object sa ibabaw ng isang spring na gumagalaw lang in one specific direction back and forth in a straight line. Yun yung tinatawag na single degree of freedom. So, dito sa gilid, may makita kayong halimbawa ng isang elastic design response spectrum. This spectrum helps engineer predict three things: how fast parts of the building might move, how much the building might move back and forth, how strong the shaking will be for the building. The spectrum show how different buildings will respond based on this natural period. Each point on the spectrum corresponds to the peak response, whether acceleration, velocity, or displacement of a structure with a specific natural frequency or period. The result is a graph that allows us to visualize how different structures, based on their natural periods, are likely to respond to an earthquake. The Elastic Design Response System helps predict how strong Now let's talk about how this tool actually works. This spectrum is created by applying seismic records from past earthquakes to a range of hypothetical single degree of freedom systems. Gamit yung mga seismic record na yun, nakakabuo ito ng isang spectrum o isang linya that shows how buildings might respond to similar earthquakes in the future. The elastic design response spectrum is typically focused on three key response types. Una is acceleration response spectrum. This shows the peak acceleration that structures of various periods would experience, and it's crucial for determining the seismic forces structure need to withstand. Or sa madaling sabi, ito yung nagpapakita on how much force is likely to hit the building. Next is velocity response spectrum. This reflects the peak velocity, helping us understand the speed of movement within the structure. Ito naman, pinapakita yung maaaring bilis na kayang igalaw ng isang building. Next is displacement response spectrum. This shows the peak displacement or the extent of movement the structure would undergo. So yun, sa building design, yung acceleration response spectrum yung pinakamahalaga. It tells engineers the potential forces that buildings must resist to prevent structural damage or collapse. So the spectrum also illustrates how structures with different periods respond to seismic forces. For example, short period structures like stiff low-rise buildings often experience high accelerations but small displacements. Meanwhile, longer period structures like flexible high-rise buildings may experience large displacements but with lower accelerations. Or sa madaling sabi, yung maliliit na buildings like small houses, they tend to feel more intense force. Ngayon naman, alamin naman natin yung mga parts ng spectrum o ng typical na elastic design response spectrum. Una, meron tayong tinatawag na rising slope. Makikita nyo dyan sa picture sa gilid yung part na may pataas na linya, yun yung rising slope. Ni-indicate nito na sa simula, the forces go up as we move to taller buildings. Sunod naman yung flat part. Yung may flat na line dyan sa graph. So, it represents the maximum acceleration which generally affects medium period structures the most. So, dito yung forces ng structure might experience at their peak. Or kumbaga dito yung may pinakamalakas na shaking ng isang building and the most forceful response. Last is descending slope. For longer period structures where the response diminishes. This means larger displacements but smaller accelerations. So dito na pinapakita yung unti-unting paghina ng force lalo na sa matataas na building. So yun, possible na din na makaapekto sa pattern yung type ng ground or soil na kinatatayuan ng building. That's why engineers also consider the local conditions when they're using the spectrum, such as the characteristics of the ground motion and local site conditions like the soil type. Sa mga earthquake-prone areas naman, national building codes often provide standardized response spectra that take these variables into account na makakatulong sa pag-decide ng structures in accordance with local seismic conditions, ensuring buildings are both safe and code compliant. So, yun lang. Ginagamit yung elastic design response spectrum kapag nagde-decide ng bridges, dams, and other critical infrastructure. Its application helps in creating
We all know na ang basic design objective ng seismic resistant design is to protect the life safety of the building occupants and the general public. Also, to control the severity of damage in small or moderate earthquakes. Kung sa elastic response spectrum, ang expected seismic performance ng building ay mag-resist ng minor and moderate level ng earthquake ground motion. Ang inelastic response spectrum naman ay kapag ang expected seismic performance ng building ay nagre-resist na ng major level of earthquake ground motion, na ang intensity ay equal daw sa strongest either experience or forecast for the building site without collapse. but possible daw na merong some structure or non-structural damage. Kailangan daw natin ang inelastic response spectrum to calculate the inelastic strength demand which should be given to our structure for a desired level of ductility. Newmark and Hall also developed a procedure for accounting for inelastic behavior in a structural system response due to an earthquake, an inelastic response spectrum. To simplify the analysis, they assume the behavior of a structure to be elastic, vertically plastic. This assumption yields a relatively accurate result and was also used to develop the inelastic design response spectrum. In this case, we solve the following nonlinear equation of motion. So, nakikita natin sa right side ng figure na meron tayo diyang mass. So, let's assume we have a mass on a trolley, which is yung M, and yung baba is frictionless, and yung mass is connected to a wall. Tapos yung wall is moving siya with displacement, U sub G, which is yung U sub G is changing with time. And connected naman yung mass sa wall with the spring, which is letter K, or F sub S U, which is the stiffness factor. Also, connected din daw siya sa dashport with damping coefficient ng letter C. So, makikita natin sa formula na M times double dot U plus C single dot U plus Fs U is equal to negative M double dot U sub G times E. So, yung mass natin na M is times siya sa total displacement na UT. And makikita natin dito sa left side ng figure na ang UT ay equal din sa UG, which is the underground displacement, plus the another displacement U, and we call it the inertia term. Next is the damping force. We found that the damping force is proportional to the velocity of the system. And the last term presenting the stiffness of the system due to the columns and beams. Kaya, equal siya sa negative m double dot g times t changing with time. The first term, m double dot u g, is what we call the inertia force. The second term is C, the single dot U is the damping force, plus yung Fs natin na U, which is the inelastic force. And itong last term na negative M, U double dot G times T is what we call the ground excitation force. Next is the ductility ratio. All other parameters are the same as for elastic system. The solution to the system requires numerical integration of the equation, and the result can be presented in the same fashion as those for the elastic case. With one major difference, the ductility of the system, which is defined in terms of the ductility ratio. This parameter is defined as ductility ratio is equal to the maximum displacement of the system, which is U sub n, over yield displacement, which is U sub y, or U sub n is equal to ductility times U sub y. In other words, mini-measure daw nito kung how much the system can deform bago niya ma-reach yung ultimate capacity. The yield displacement or the U sub y is the displacement at which the system begins to behave non-linearly. It is typically determined by the yield strength of the materials. And the ductility ratio is an important parameter for designing a structure that are subjected to seismic loads. It is used to ensure the structure can withstand the expected seismic force without collapsing. A high ductility ratio indicates that the structure is more resistant to damage. We can also define a parameter based on the fictitious corresponding linear system and the yield force known as the yield strength reduction factor Ry. Ry is equal to F sub O or F sub Y equals K, which is the stiffness factor, U sub O over K, U sub Y. Then, um, cancel natin tong K, kaya magkakaroon tayo ng U sub O over U sub Y. And U sub O represent the maximum displacement of the corresponding linear elastic system. In addition to ductility, we can define a second displacement ratio between maximum displacement U sub M and the maximum displacement of the fictitious corresponding linear system U sub O, which relates R sub Y and ductility. So, dito is U sub M over U sub O is equal to U sub M over U sub O times U sub Y over U sub Y equal sa ductility times U sub Y over U sub O or equal din sa ductility over Ry. This gives the ductility demand imposed on an elastoplastic system by ground motion and kaya naging ductility is equal to U sub M over U sub O times R sub Y. Makikita natin dito sa left side na figure is the elastoplastic response spectra for L-centric. This figure clearly indicates that damping has a decreasing effect as ductility increases and is much less effective than ductility in reducing the maximum response. Furthermore, to increase system earthquake resistance, it can be designed by either making it strong or ductile, or a combination of the two, because increasing ductility greatly decreases response. In conclusion, while ductility is often considered a primary strategy for earthquake resistance, damping can play a valuable role, especially when combined with other design measures. The optimal approach will depend on a variety of factors, including a specific characteristic of the structure and the seismic hazard. Given yield displacement U sub Y, the relationship between elastic and inelastic quantities are as follows. D sub y is equal to U sub y, which is the yield displacement. Vy is the side velocity, which is omega n times yield displacement. Ay is the side acceleration, omega n squared times yield displacement. And ang omega n squared daw natin dito is equal siya sa 2 pi over Tn squared. And since yung mga nauna natin na formula is U sub M is equal to ductility times U sub Y or U sub M is equal to ductility D sub Y, magkakaroon tayo ng another formula na UM or the maximum displacement is equal to ductility times T sub N over 2 pi squared times side acceleration.
Yung mga structure ay dinedesign siya considering yung capacity nun to resist inelastic deformation. So, kailangan natin ng inelastic design spectra sa pagde-design. So, kung sa elastic design response spectrum is gumagamit tayo ng backbone ng peak ground properties and ina-adjust yung mga values na yun gamit yung amplification factor. Sa inelastic design response spectrum is gumagawa tayo ng new backbone ng elastic spectral response properties and bagong set ng adjustment parameters na para sa inelastic behavior. So, yung mga adjustment parameters na yun are functions of system ductility. So, magsisimula tayo sa ductility ratio. Ductility ratio is equals to the maximum deformation over the yield deformation. And deformation is equals to the coefficient of stiffness times force. Then, cancel yung K, matitira is F sub E over F sub Y. Then, kung makikita natin sa figure sa gilid, Fy is equals to Fi. kaya naging F sub E over F sub I. Then we know that force is equals to mass times acceleration, kaya naging ganyan. Then cancel yung M, ang matitira is acceleration sub Y over acceleration sub I. So dahil dyan, this results sa maximum inelastic acceleration equals sa maximum elastic acceleration divided by the ductility factor. So, yung equation na nakuha is para lang yun sa may constant displacement in region pero hindi pwede sa constant acceleration region. So, para sa constant acceleration region is i-equate natin yung elastic and inelastic. So, yung mga susunod na slide is para lang makuha yung yield deformation. So, feel free to pause. So, gamit yung nakuha nating yield deformation, makukuha natin yung maximum inelastic deformation. So, andyan na yung mga formulas. Ito naman yung mga formulas for the maximum displacement and yung maximum force or yung required yield strength. Problem, consider the building frame shown in the figure with 5% damping and IS is equals to 75 inch raised to 4 for the two columns subjected to a ground acceleration due to an earthquake characterized by the 84.1% design spectrum scaled to 0.5 G PGA. Assume elastoplastic behavior and determine the lateral deformation and force for which the frame should be designed if deformation is equals to 4. So that mahanap mo muna yung mass and stiffness constant. So yung mass is equals to weight over gravitational acceleration. So, ang makuha natin is 3.88 pounds second squared per inches. Then, yung K, yung formula na yan is kapag yung column ay fixed at hinge. So, ang makukuha is 2,237.6 pound per inch. Then, makukuha mo na yung natural period of the system, which is 2 pi times square root of m over k. Ang makukuha mo ay 0.262 seconds. Based sa problem natin is 84.1% percentile and may 5% damping tayo. So, 2.71, 2.3, tas 2.01 lang yung pagpipilian natin. So, since yung nakuha nating natural period ay nasa acceleration sensitive region, so ang gagamitin natin is yung 2.71. So, times lang natin yung 2.71 na yun dun sa 0.5 G na PGA. So, makukuha natin is 1.335 G. So, nakuha natin na yung A, so makukuha natin yung maximum displacement. So, ang makukuha natin ay 1.353 inches. So, since given naman na lahat, makukuha mo na rin yung force na 770 pounds. Next example problem is ito na yung paggawa ng inelastic design spectra. So, construct using Newmark-Hall approach an inelastic design spectra for 5% damping and the ductility factor of 3 for a soil site where the expected peak ground acceleration is estimated to be 0.16 G. Use the amplification factors corresponding to the mean plus 1 standard deviation. So, dito hanapin natin yung peak ground velocity and displacement. So, may given tayong peak ground acceleration na 0.16 G and yung G natin is 386.4 inch per second squared. Makukuha natin yung velocity gamit yung V over A is equals to 48 inch per second per G. So, 48 times 0.16, makakancel lang naman yung G since may G dito sa taas. So, 7.7 inch per second. Sa displacement naman is yung AD over V squared is equals to 6. So, D is equals to 5.8 inches. So, ito yung amplification factor. So, may dalawa yung 1 sigma and yung median. So, nakabase tayo kung ano yung given, then yung given na damping. Then, may alpha dito na tatlo. Alpha for acceleration, velocity, and displacement. So, dyan natin tina-times yung mga peak ground velocity, displacement, and acceleration para makuha yung elastic spectra. So, ito na yun, elastic spectral accelerations, velocities, and displacements are yan. So, tinimes mo lang yung alpha niya dun sa peak ground. So, para makuha mo naman yung inelastic spectra is gagamitin mo lang yung na-derive mo kanina na yield deformation na U sub E over square root of 2 ductility ratio minus 1. Then, substitute mo lang. So, yan na yung design spectrum ng example problem.